In our next section, we're going to continue our discussion of UCS LAN connectivity for the Blade Series chassis, and specifically talk about how we form regular Ethernet port channels from the fabric interconnects to the northbound network. And one of the key points about this section to understand is that when we look at the physical topology, we see that we have multiple connections from the northbound switches, in this case our 5K1 and 5K2, down to the FIs. So from the 5K's point of view, we're going to be configuring a VPC domain, a virtual port channel. So the 5Ks are going to have an east-west link between each other that is synchronizing the control plane. Like we talked about before in the VPC section, this is called the VPC peer link, mainly used to synchronize the MAC address table and then other options like IGMP snooping, ARP cache, and so on and so forth. But the key point to understand about the UCS is that even though we do have that east-west connection, the L1 and L2 link that is the cluster link for the configuration, remember that the UCS fabric interconnects are not sharing the same control plane. So this means that even though we have that east-west link between them, we cannot configure a VPC down to the servers. Now we can configure regular port channels northbound, and what we're going to be doing in this example is that we're going to have two separate port channels. So one of them is going to be going from fabric interconnect A on physical uplinks E1, 3, 4, and 5. These are going to 5K1 and 5K2 respectively. So from 5K1 and 5K2, we're going to have the east-west peer link that's running as a layer 2 port channel. We're going to have the keep alive. In this example, we'll use the management port to form the VPC domain. And then from the 5K's point of view, we're going to have two port channels that ultimately are going to be matching the UCS. So physically, from the 5K side, this is going to be ports 9 and 10 on 5K1, and then ports 11 on 5K2. Okay, so 9 and 10 on the left here, port 11 on the right. These are going to form our first VPC, so we'll say that this is VPC just number 1. Okay, this is going down to Fabric Interconnect A. And then we're going to have a second VPC that's going on from the FI's point of view. This is going to be ports 3, 4, and 5 on Fabric Interconnect B that are going northbound to ports 9 and 10 on 5K2, and then going over to port 11 on 5K1. So a key point here is that from the UCS Fabric Interconnect point of view, they're going to see just two regular Ethernet port channels. They don't know that they're connected to a VPC domain northbound. So we could be going to two separate physical switches. In this case, we're going to, or I should say, two physical switches that are not clustered together. Okay, so not a VPC, not a stackwise, not a VSS. They could be two independent switches, and the behavior is going to be same from the UCS point of view. Now, one of the documents that I had mentioned before in this section for further resources outside of the class was the UCS Technology Design Guide. And I want to go back briefly through that and talk about what are the typical design options for both UCS LAN connectivity and SAN connectivity, and then see how that's going to apply to our example here. So you want to go to find this document, you want to go to cisco.com/go/CVD, Charlie Victor David. It's for the Cisco Validated Designs. Then under the design zone, we're going to go down to all design guides. Either all guides here, or you can go down under data center networking. And then under data center networking, we go to Cisco Validated Designs. And this is the Unified Computing System Technology Design Guide. So I would definitely recommend to read this through end to end. Essentially what this is like a field deployment guide that if you got the UCS, you're pulling it out of the box, you're physically rack mounting it, physically wiring it, and then doing the configuration. It walks step by step through not only the deployment details, so how do you configure storage, how do you configure networking, but it also talks about just some general background information, what are the components of the system, what's the overall design that we're trying to achieve in addition to the actual implementation. Okay, so what we're going to focus on here is the deployment detail. So I would definitely recommend to read through the introduction just to talk about the design overall. But then under deployment details, they have this broken down into three major sections. So we have the network infrastructure, which in our case is going to be LAN connectivity. We have well, actually, network infrastructure is 2 points. So it's Ethernet connectivity and then storage connectivity. So LAN and SAN. And then the second portion is going to be physically connecting the Blade system and then the actual configuration. Okay, like how the service profiles work, how did the boot policy work. Again, these details we're going to be coming back to in later sections as we talk about the different pools and policies that you can apply under the UCS. So we've gone through some basic examples of just how do we configure standalone service profiles. Later we'll be coming back to this and revisiting how do we deal with service profile templates, what's the difference between a standalone template versus an updating template, how do you make copies or instantiate the template, how do you change the individual options of a service profile instance that you spawn from the template, and so on and so forth. But as this relates to LAN connectivity and SAN connectivity, they show a couple diagrams here that are going to pretty closely mirror what I'm doing in this example. So it says, first off, for Ethernet connectivity, they recommend that you configure a virtual port channel, assuming we're going to Nexus 5Ks. So we have a virtual port channel on the northbound side, which in our particular case, this is going to be 5K1 and 5K2. So they have multiple links that are going down to the fabric interconnects. And from the fabric interconnects point of view, we're going to have two separate port channels. So they have port channel 50 on the A side, they have port channel 51 on the B side. And then from the 5K's point of view, these would be VPC 50 and VPC 51 respectively. So a key takeaway here is that you cannot configure a back-to-back VPC or a double-sided VPC, because even though the fabric interconnects do have that cluster link is only exchanging the config. So it's only for synchronizing the management plane. It's not for synchronizing the control plane and the data plane. So you can't have any actual packets, data plane packets like web browsing, for example, that would be forwarding through the cluster link. Okay, so beyond this, it shows what are the specific config details. So we'll go through this again real quickly on the 5K side. So that would be the VPC config. They move on to say for storage connectivity, we're going to have either one of two designs, either native fiber channel or FCOE. But the key point about this is that the physical links that are going from the fabric interconnects to the northbound switches are going to be dedicated only for SAN traffic, and we're not sharing both SAN and LAN connectivity. So down to the access layer, down to the actual blade server or the standalone rack mount server, in the case we're dealing with C-series servers, both the LAN and SAN connectivity are going to be unified on the same physical ports or the same physical wire. So if we think about the blade system beyond the chassis, we go down from the fabric interconnects to the I/O module. We have I/O module A, we have I/O module B, and then we saw from our global connectivity policy, we can configure this as a port channel from the FIs south to the IOMs, and then the I/O modules are going to have multiple connections inside the blade chassis that are actually going to the server, like blade number 1. But we'll see that from an OS level, the blade OS is not going to be able to form a port channel between these two links and then load balance per flow. Now, we will see in some later examples when we're talking about Nexus 1000V, the VMware Distributed Virtual Switch, and then also the Cisco Application Virtual Switch, the AVS, as it integrates with the 8-bit controller for ACI, that if we are doing a port channel at the OS level, we need to make sure that we are doing static MAC pinning on a per virtual machine basis. So let's say that on this particular blade, we have some sort of hypervisor, either ESXX, ESXi, Microsoft Hyper-V, KVM, whatever, and we have two different virtual machines. So we have virtual machine A, we have virtual machine B. From a load balancing point of view, we would need to make sure that the A virtual machine traffic goes to the left and the B virtual machine traffic goes to the right. So we're not able to load balance this on a per flow basis like you would a normal port channel. And again, ultimately the reason why is that Fabric Interconnect A is going to have a different MAC address table than Fabric Interconnect B. So they're not syncing the control plane between each other. Okay, so let's take a look at the, actually let's start at the Fabric Interconnect CLI. And let's see what the current state of the network is in terms of both the storage connectivity and the LAN connectivity. Okay, so let me open up my terminal software, and then we're going to telnet to both of the 5Ks and then also Fabric Interconnect A and B. And remember, the reason why we're doing both of these is that every time you make a config change, you pretty much have to do it twice. Okay, once for the A fabric and once for the B fabric. So let's log in as admin. Password I set was CCIEDC01. And then from the FI, we're going to say connect NXOS. This is going to get us into our Nexus CLI that we can look at, let's say like the show interface brief. Okay, this shows our storage connectivity. In this case, we have fiber channel 1/31 and 32. These are running as proxy ports in vSAN 101. And then on Fabric Interconnect B, we should see a similar output, but main difference is that we're running vSAN 102 on Fabric B. We're running vSAN 101 on Fabric A. So for these examples, we're not going to get into any more details of the storage connectivity. If you want more information on this, I did cover this in more detail in the storage switching section. So in terms of the native FC port channels, the FCOE uplink port channels, the unified uplink port channels, what are the different variations from that? But we're assuming at this point, the servers do have connectivity to the remote disks on the storage array. What we're mainly concerned with is what happens when the OS actually boots, and then we start to run the network drivers for LAN connectivity. How are they going to have reachability to the upstream network? Okay, then we saw from the diagram additionally that the physical links E11 and E12, these are our fabric ports from the FI's point of view that are going downstream to the I/O module. Okay, I/O module again is analogous to the fabric extender within the case of the 5Ks and the 2Ks. And then the I/O module ultimately is connecting us behind the scenes to the blades. So if we were to go further down here, we should see Ethernet 111 through 1132. And these interfaces, these are running as VN tag. These are the links that are going southbound to the blades. So from a VLAN point of view, like if we're trunking multiple VLANs, Ethernet VLANs down to the blades, the key point here is that behind the scenes, the actual network adapter that the server is using, so the VIC 1240, VIC 1280, 1340, 1380 in the newer blades, that understands the special virtual networking tag or the VN tag format that the I/O module is sending down to the server. So ultimately, the adapter knows what type of traffic is going to relate to storage, what type of traffic is going to relate to LAN, and then within the LAN traffic, what are the individual VLANs that we're forwarding down to the actual OS, whether this is a hypervisor or whether this is bare metal. The actual adapter itself has to understand the VN tag, which means generally that we're running the Cisco-specific adapters, like I mentioned, VIC 1280, VIC 1380. Okay, what we're now going to be concerned with is that if we look at the show interface brief, and we're going to pipe to include capital VETH for virtual interface or virtual Ethernet. And what these interfaces are going to correspond to is both the storage adapters, so the virtual HBAs, and the network adapters, the virtual NICs, that we're assigning from the I/O module southbound to the blades. And we can also see for the storage adapters, we can see what the mapping is between the virtual fiber channel interfaces and the virtual Ethernets. So we see 8892, 8896. These ones are going to be used for storage. And notice that they're using VLAN 101, which on Fabric A is mapping towards vSAN 101. Okay, or in other words, these virtual Ethernets, these are going to be used for FCOE. Then we have regular LAN adapters. We have them in VLANs 10 and 20 that are going to be used for the regular IP traffic that is going down to the end hosts. Now, we also talked about the difference in terms of the control plane decision of how does the FI know where to forward traffic when it's coming from the blade, so from the southbound network, and then going north. So going from the blade to the I/O module, from the I/O module to the FI, from the FI to the northbound switch. Since we're not running spanning tree, it means that we're not doing a normal destination MAC address forwarding decision like we would a regular Ethernet switch. And instead what we're doing is looking at the static pinning decision of the virtual Ethernet to figure out what physical northbound link are we using in order to reach the LAN connectivity. So if we look at the show pinning, we saw three variations of this. We can either say show pinning border interfaces, server interfaces, or the specific link, like show pinning for interface VETH 698. And this is going to tell us what our physical upstream interface is. In this case, we have a pin group, a LAN pin group assigned to the virtual NIC. So it says that it is hard pinned, or essentially like statically routed for traffic coming from this blade, we're exiting on port Ethernet 1/4. So if we were to look at the show interface vEth 698, okay, actually show interface trunk, or actually I think it's show interface vEth and then trunk at the end. So show interface vEth trunk. It says what VLANs are allowed on the trunk. Let me see if I can fix this out, but it looks like terminal with 511. Okay, so it says that we have currently VLAN 20 is allowed on the trunk, and this is specifically bound to chassis 1, server number 5, and its virtual NIC named ETH0. Okay, if we look at the same thing for the next number, which I believe was 702. Okay, 702. So let's show interface vEth 702 trunk. Okay, this is trunking VLAN 10. This is assigned to chassis number 1, server number 4. So ultimately, once we're done with this next step, which is configuring the port channels, we should see that the pinning of both of these vEths is going to change to point to the logical port channel as opposed to pointing towards the physical interface. Now, the advantage of that is that if we want to add more links from the fabric interconnect to the northbound switches, or if we have a failure where one of the optics fails, the physical link fails, it means that the downstream server will not need to repin, or in other words, we still have connectivity on fabric A, we still have connectivity on fabric B, as long as one of the physical interfaces remains in the port channel. Now, beyond this, we'll also talk about further failure scenarios. What if we lose the entire fabric interconnect, or what if we lose the entire northbound switch? What happens with traffic, LAN traffic that was forwarding on fabric A? How do we fail it over to fabric B? And then how does that affect the underlying OS? But for this example, what we should see is that when we look at the show pinning for the border interfaces, okay, border interfaces, in this case, we have Ethernet 3 through 7. We should see that interfaces 3, 4, and 5 are going to be gone from this output. These are going to be replaced with a logical port channel, and then ultimately all of the vEths are going to be pinning to that port channel. And same should be true on fabric B. So if we go to FIB, we look at the show pinning for the border interfaces. We're going to be using interfaces 3, 4, and 5. Okay, so next let's go back to the UCS GUI.